traveling salesman problem. The problem is to find the shortest tour through n cities that visits every city exactly once. In order to find this shortest tour, you are required to find the shortest Hamiltonian circuit of the graph. Now we'll see what is Hamiltonian circuit. Hamiltonian circuit is defined as a cycle that passes through all the vertices of the graph exactly once. Now we'll see how to solve this problem using branch and bound design technique, because this is combinatorial and optimization problem. Since it is a minimization problem, because you are required to minimize the tour length, you are required to find out the lower bound. Lower bound equal to CL of S by 2. Now we'll see how to find out the lower bound initially. So tour starts with A here. From A, you can reach to city B and C with minimum tour length. That is, A to B it is 3 and A to C it is 1. So from A, best possible values are 1 and 3. Similarly from B, 3 and 6. From C, it is 1 and 2. From D, it is 3 and 4. And from E, it is 2 and 3. So the same thing is being written. Total is 28 divided by 2 is 14. This is the lower bound you can achieve, or this is the least possible tour length you can achieve for this given instance of the problem. Now from A, you can go to B, or you can go to C, or you can go to D, or you can go to E. We'll see all possibilities. So in case you go to B, what is the lower bound? And in case if you go to C, what is the lower bound? And D, and for E. So that is, we'll see how to calculate that. Now from A to B, if you want to decide to go to B, then AB if you include, and BA also should be included. A to B, B to E must be included. For the node A, AB is included. So similarly, you include BA here. Okay, so this is similar to the first one only. First, what you have found the lower bound, the same values. Total will be 28 divided by 2 is 14. And in case if you decide to go to C, then the lower bound can be calculated like this. 1, AC should be included. Similarly, CA should be included. If you include that, there is no difference here. Whatever you have calculated the lower bound initially, the same thing. Therefore, this is equal to 14 only. Again from A to D, if you decide to go to D, then DA also should be included. Okay, AD, DA. Replace AB with here AD, and here this 4 is replaced with DA value, that is DA is 5. Look at here, here to here there is 2 difference, here 1, that is 3. There is an increase in 3, so add 3 to this, 31 by 2, that is equal to 16, because you are required to take the CL of this value. And from A to E, if you want to go, then AE should be included. Here from A, the first minimum choice is 1, and instead of taking the minimum value, what I am taking is A to E, because we are deciding to go to E. AE I have considered, include that AE. Once you have included AE here, and EA also should be included. So in the node E, you have to include the HEA. So replace this 3 by 8. So here there is 5 increase, and here 5 increase, totally 10 increase in the value. Add 10 to this, that is 38 by 2, it's equal to 19. Look at here, if you decide to go to B, then the lower bound is 14. If you decide to go to C, then it is 14. And if you decide to go to say D, A to D, then it is equal to 16. Then from A to E, the lower bound is 19. Same thing is written in the state space tree. A to B, A to C, A to D and A to E. And A to C also same thing, lower bound equal to 14. But since B appears first, so we are considering this node. With this we are extending the branch. Okay, so here AB, AC, AD, AE, out of all these 4 nodes, this is the best choice we have made. So from here I'll just branch out. Once you decided to go to B, you have only 3 choices. Either you go to C, or you are required to go to D, or you are required to go to E. Okay, so calculate the lower bound. In case if you decide to go to from B to C, then BC, CB should be included. That means in the node B, consider the first lower bound what you have calculated here. The same thing you consider here, because for A, for the node A, 1, and we decided to include AB. HAB is included here. And for B, again, AB is to be included. AB is the must and should edge in for the node B. And from B, you need to go to C. So here if you go to C, 6, the length of the edge is 6. And from C, you have to include CB also. So CB. If you include that, it is 6. Here there is no increase. Here there is an increase in 4. Therefore add 4 to this, 32 by 2. It is 60. Okay. Next, from B you can go to C. Then the lower bound will be 16. If you decide to go to D, we'll see what is the lower bound. B to D is 7. When you include 7 here, even D to B must be included here. So here D to B is included here. So there is an increase in 1 unit. Here 3. 1 plus 3, 4. For this, add 4 to this value. It's equal to 32. 32 by 2 is 16. Again here you are required to find out the lower bound. From B, if you decide to go to E, then here include BE here. If you include BE, the length is 9. And here for the node E, you have to include EB. 9, 9. Here for 6, there is an increase in length 3. Here there is an increase in length 6. 3 plus 6, 9. For this, if you add 9 to this, 37. 37 by 2 is actually 18.5. Since you are taking seal of this, it will be 19. The same thing, that is, if you decide to go to C, lower bound will be 16. If you decide to go to D, lower bound is 16. If you decide to go to E, lower bound is 19. Same thing is written in the state space tree. These two are the best possible values. Okay, so we'll see the optimal tour length. Since ABC, from A to B, B to C, you decided here, from here to here, A to B, and from here you have taken a decision that it's a best possible value, that is A to B, B to C. So once it is decided to reach to C, then only 2 cities is left out, that is D and E. Either you have to go to D first or E first. So once you go to D, then obviously you are required to go to E. This is the only remaining city. Then you have to go back to A. Here A to B, B to C, C to E, and then you have to go to D, and then you have to come back to A itself. Similarly, if you have decided to go to A to B, B to D, then the alternative is, look at here, A to B, B to D. The left out cities are C and E. Obviously, from D to C, if you decide to go, then the left out city is E. You have to go to E and then you have to go back to A. Then the other alternate solution is A to B, B to D, D to E, then C to A. Like this. We'll see what are the tour length here. No need to find out the lower bound because here you have only two choices. When you have only two choices, either you have to go to first city or second city. Once you have decided to go to one of these two cities, then the left out city you have to visit because there is no other alternative. Then you have to come back to the city with which you started the tour. So this is what you are required to do in this. So we'll see how this value is achieved in this diagram. A to B, A to B, B to C, C to D, D to E, and E to A. Then the tour length is 24. If I do the tour like this, A to B, B to C, C to E, it is A to B, B to C, C to E, E to D, and D to A. Tour length is 19. Then from A to B, B to D, then D to C, C to E, and E to A. Tour length is 24. And here from A to B, B to D, D to E, and E to C, C to A, tour length is 16. So these are all the possible tour lengths with its lower bounds. But this is not optimal and this is much better, but this is the optimal tour length. That is how you need to travel from A to B, B to D, D to E, E to C, and C to A. In case if the traveling salesman travels the cities in this way, he can achieve the tour length equal to 16. This is how you can find the solution using traveling salesman problem using branch and bound design technique.